Like a nice sunrise color. Why is it orange today? Yesterday it was like purple.
I'm going through the rainbow.
Well, in other classes, they use a true display, emitting display, and then there is a source that reflects the face. Then the quality is better. And here it's the same, like projector is source of light, and therefore it interferes with lamps. And you all who will stand here will look. So,
Oh.
Can you please also project the camera onto back screen? And keep the computer conference here. Okay, excellent. Thank you so much. Well, many thanks for coming. So today will be a special meeting because the lecture will be presented by attendees of the class. So here are your notes, and now you see why I was asking you to prepare them a little bit ahead of time and send them by midnight. So it takes a little time to look through,
I forgot to put your name on it.
make objections to you if something is wrong, and to print ahead of time. So if you would be sending it like 5 minutes before the start, it would be too late. So, who we are, what are we doing, and what is our goal? So, it is a physical chemistry class that it is based in on the based on what? On quantum theory. That is one of the counterintuitive theories that contradicts with common sense. Therefore, we do a slow start and do it not immediately, but slowly but surely. So we have practiced slow start for about 6 meetings, and now we summarize this slow start with presentations of the summary of the background of quantum theory, which is known as postulates. We do have 7 groups presenting, 7 mini teams presenting on the subjects about postulate about wave function, about observables, about measurement, expectation values, and how observer changes the system. What is time dependence? This was main focus on our lectures. And then there will be another team that will provide a little bit of additional mathematical background that we will use in the rest of the course. So it is supposed that each of us, including me, speaks no more than 5 minutes plus questions, ideally 3 minutes, and then everyone is invited to ask questions to the presenters. This material will not be covered in the rest of the class, so if something is not clear, take your chance and ask the presenters. The idea is one person becomes an expert in one subject, another person in another subject, and then we exchange our expertise through this verbal interaction as much as it is possible. So, practically, how do we arrange it? So, there is a computer with standard mouse, keyboard, and touch screen. So your presentations are on the desktop, 1, 2, 3, 4, 5, 6, 7. And if you hate numbers, there are names. So you recognize you or your partner. So you click, it comes up, And then there is a symbol to start presentation. If you are not a PC person and you prefer Mac or Linux, so this is a symbol to start. So with this, I would like to invite first two speakers, Hannah Fanus and Austin Breuer, to present their subject on postulate number 1. Okay, I start the stopwatch. And you can see on the back screen if you are in the focus of the camera. Whenever you want to be in the focus or avoid it.
Set. All right, no golf clap when we came up. My name is Austin, and so our postulate is quantum mechanics postulate number 1. And just stating kind of the main goal of this postulate, since this class is all about goals, what we're looking at is just basically trying to prove that something exists in space and time. And for us, that's going to be that electron or that wave formula or wave particle that's in that in space and time. So that's essentially what the definition of postulate 1 says. It's the complex wave function multiplied by the wave function itself comes to give us this determination that there is a particle at some space and some time dictated by dx, xo, and t0. It works with any variable, so if you were to take all space and time, dx, dy, dz, take the integral of both the wave functions, you're able to find that the probability that there's some kind of particle or wave function in this space is going to be exactly equal to 1. Essentially, giving a really common example, if I'm standing in this room, there's a 100% possibility that I'm standing in this room. Exact same thing, there's a 100% possibility that there's an electron somewhere in space and time. What this really kind of comes down to and why it's important to quantum mechanics is that we get these observables that we can get from that. Since I'm standing in the room and there's some existence of me in the room, you can take things such as my height, my weight, things like that. In the same sense that you can do that for quantum particles or wave functions, you can take the observables from them and figure out what you need to, such as momentum, angular velocity, things like that, and get those observables to dictate other equations, which the mathematics is what Hannah will take us into right now.
He kind of touched on this a little bit, but normalization is kind of the scaling of the wave function, so that the probability over all space is equal to 1. And then so you see the integral of the complex conjugate of the wave function times the wave function dx is equal to 1. And then that's kind of saying the same thing as the magnitude squared is equal to 1. And these are just the conditions for that probability function to work. And so it has to be a single valued function. So for each position in space, the x, there's only one position in time, t, associated with it. So like this graph of the wave function would be a single valued function. And also the second derivative of the wave function must exist to set up the Schrodinger equation. And also for this probability function to work, the function must be continuous, meaning f of x is defined at a, the limit of f of x as x approaches a exists, and the limit of f of x equals f of a. Yeah.
So it's really, no, go ahead and summarize it here quickly if you want.
Okay, so kind of the summary for all this is it allows further postulates to be developed because it gives support that the particle or wave function exists somewhere in space and time. This gives us as chemists the possibility to find observable measurements in quantum mechanics. Can I do last two? Or?
Yeah, for sure. Basically, what it comes down to is that our postulate's the best, and it sets up all the rest of your postulates. It just basically states that there's something in existence that we can find and we can observe, which helps us create equations that aren't affected by things such as complex values or anything like that. It still is dependent on time, which is a factor that we have to take into consideration when setting up other equations. But again, it's just one step forward to getting measurable quantities for quantum mechanics, wave functions, and particles in space and time.
Okay, let's thank the speakers. And it is your chance to ask them something. I do have one question.
Yeah.
So you were mentioning, or you wanted to mention that wave function square is probability.
Mm-hmm.
Then what is wave function when it is not squared? Does it have any meaning?
When it is not squared? the wave function itself would just be like a single value, not of the probability, but it'd be
Like the graph, the wave function.
Well, you shouldn't
well, it
be.
wouldn't include complex values or anything like that. So it would just be, it wouldn't be all the sets or standards of what the entire universe holds.
It is okay to say that wave function itself doesn't have physical meaning, is not related to observable.
True.
You always need to find the expectation value or square.
Right.
And the term for wave function dimension is amplitude of probability, if you want to. More questions to the speakers? If no, let's thank them once again. So, and thanks them for being good in time. So, next team is by Megan Schneider and Luke Wollman for postulate number 2, observables and operators.
Did everyone pick that game, I'm guessing?
Okay, so this is postulate 2. And the definition is for every classical observable, there corresponds a linear Hermitian quantum mechanical operator. So a classical observable is something that you can see with your own eyes or measure yourself in a lab. And examples of a linear operator is any x to the nth power, taking the integration of something or the nth derivative of something. And a Hermitian requires the properties to be real. So an example of an observable is total energy, which has the symbol of capital E, and the operator of the Hamiltonian, which is the negative of Planck's constant squared over 2m, and the square root of the partial derivative plus b. The Hamiltonian we've already seen in the Schrodinger equation. And there are many more examples of operators on the table 4.1 handout, but I'm not going to read them all to you. In the last lecture, we discovered the example of momentum and its operator, which would also fit under this postulate. For a Hermitian operator, the eigenvalues have to be real, but therefore if the eigenvalues are real, it is a Hermitian operator. And that observables have to be real properties that you can measure. So for example, if we take the linear operator, write down the expression in position coordinates x, y, and z, and the linear momentum coordinates of p sub x, p sub y, and p sub z, and replace the coordinates with their operator. So for position in one dimension, our operator symbol is x hat, and what we operate is just multiplying by x. So if you take it and you integrate it a few times and eventually simplify it, you find that x hat equals itself, because x hat is real, and that proves that it is a Hermitian operator. Although there's an important note, the order in which the operator is applied is important. If we have the wave function of sine of x, and we multiply it with p sub x times x hat times sine of x, then we get negative I, the Planck's constant, sine of x plus x cosine x. But if we multiply it in the opposite order, we get negative I Planck's constant x times cosine of x. These are different, although not all Hermitian operators cause it to be different in the order we apply it, but it's important to note that most of them do.
Okay, let's thank the team. And it is your chance to ask something about operators.
Sure.
Questions 1, question 2, I do have. So, try, it is boring just to sit and listen, design questions while they're speaking. So, can operators exist without wave functions? Do they make sense without wave functions? What are connections? What are at least 2 connections between operators and wave functions from previous talk? Just try to, any thoughts you have on this subject? Connection, operator to wave function.
The operator is applied to the wave function.
Yes, perfect. It's connection number one. Good. And any other?
Not
No.
on the
Okay.
spot right.
So when we will go through the rest of the talks, you will see the main thing, main statement of this set of postulates. So the operator is a bridge between quantum theory and wave function and observable for the real world, what we get on experiment. So first, to change wave function to affect it. Second, bridge to real world. Last chance for the questions. If not, let's thank the team once again. And the next presentation will be, it's my chance to learn your names, by Beth Spadol and Aaron Polensky. And they will present postulate number 3. What a good coincidence, it's top number 3. On the measurement.
Alright, so we had postulate number 3, and it just states that any measurement of an observable property A will only yield eigenvalues of the quantum mechanical operator A hat, and any observable property is like any measurement you can actually take and find, so energy, position, momentum, anything like that you can actually measure.
Okay, so the equation that postulate 3 gives us is right here. So it states that the operator is applied to a wave function is the same as a constant times the same wave function, where the constant has to be a real number because, as Megan stated, it has to be an observable property. The set of our wave functions are also called our eigenfunctions of the operator. So that's what is being taken, or the operator is being applied to. And then the set of our constants is our eigenvalues of the operator A.
And then we can only measure values of that property that belong to the set of eigenvalues for that property. And then if the wave function equals some specific eigenvalue, psi equals psi, the wave function and initial, then the only value we can measure is the eigenvalue of the individual eigenfunction.
Yeah, so basically what that's saying is that, so in the previous equation, it was for any set of wave functions. This is saying if we choose a specific wave function, then we can only get the eigenvalue for that specific wave function as opposed to the entire set of eigenvalues. And then down here, it's the final equation for this postulate. It's saying that our wave function can be a linear combination of these eigenfunctions. So it is the sum of all of the eigenfunctions put together into the wave function, where the constant is not equal to 0.
Yeah. Okay, let's thank the speakers and the team. So what did you want to ask them about measurements, operators, and eigenvalues? Questions 1, questions 2. I do have a couple. If you don't want me to speak, ask your questions. Help your friends. So you already told it. I would like you to highlight it once again for the class. What is the connection between eigenvalue of operator and results of measurement on experiment? You told it.
Well,
Yeah.
about this. So,
Okay, let me simplify the question.
yeah, I don't know what you're asking.
Would you agree that there is some connection between eigenvalues of operator and results of measurement?
Yes.
Great, nice answer to the question. Okay, so another statement, and they just hesitant right now, that eigenvalues of operators, it is what is being measured in the instruments. That's good. They told it, I believe it. But it will be measurement of this kind only if wave function was prepared in the eigenstate of this operator. But what if a bad guy came and broke the wave function so that it became a wave function in a superposition, as in your last slide. What will be the outcome of the measurement?
It would be just the wave function.
No. In the measurement, you can get only eigenvalue, not the function.
Yep.
So what would you measure?
You would measure only things that would relate to that.
What? Can you repeat?
No.
Okay, let me help them. It is a very provocative, very tricky question that made many people insane in the past. So the statement is postulated, it has not changed. You still will measure one of the eigenvalues. But from time to time, if you repeat experiment, you will measure either one or another eigenvalue. So in average, you need to repeat experiment with this corrupt wave function again and again and make statistics. Do you have objections?
No.
So you sign, you agree with this answer. Thank you much, and let's thank speakers once again.
Can I ask one more question? I found a question.
Only to the speakers.
Yes.
It's not my time to answer questions.
Okay. So you said that the wave function is a linear combination of the eigenvalue functions, right? Or the eigenfunctions.
Mhm.
So isn't an eigenfunction just a scalar representation of the same wave function? How do you get a linear combination out of that, or am I misunderstanding something?
So I guess I think if I'm getting your question, that's what that equation was saying. So the operator applied to the wave function is the same as the constant applied to the same wave function.
Gotcha. Cool.
Does that answer
That'll work.
it? Okay.
In some cases, you will be correct. No, Jay. Okay. Next presenter,
I'm Landon. Luke is not here.
Landon Johnson. On behalf of Luke Beering. Postulate number 4 about expectation values. So it is in very tight relation and connection to previous presentation and my provocative questions.
That's right.
So
So I suppose I should mention what the difference between an expectation value and an average is in quantum mechanics. So in quantum mechanics, when you observe a system, what will happen is you're actually going to disturb the wave function, and whatever it is that you observe, the function will collapse that you keep getting that same value unless you wait for long enough. So what the expectation value is it's more of the average over an ensemble of identically prepared systems, so that you can just basically check the one, check the other, so you don't have to worry about the collapsing wave functions. So it's essentially just an average with a caveat. So I guess this is what the form is. So I took this example from Introduction to Quantum Mechanics by Griffiths. So we're going to let n equal the total number of people in the room. J is the age of whichever person, and n of j will be the number of people in the room that have that particular age j. And if you'd like, you can think of this as like position or anything else that you can represent with a scalar quantity. So the total number of the people in the room, if you sum over every possible value of their age, I should have probably mentioned that we're summing over j here, in all of the sums, I believe.
and some of us are of the age minus infinity.
Well, yeah, I just did it like that just to make it more general. Because if you're thinking about like position or something like that, you know, if you sum over every possible value that there could potentially be, then you'll get the total number of people because, I mean, you've added every person of every possible age or of every particular position. So then the probability of picking someone with a, you know, a given age would be given by the number of people at that particular age divided by, you know, the total number of people. So then, if we normalize this probability, we get the constraint that if you sum over every possible outcome, you have a 100% chance of finding somebody of that age because you've looked at everybody. So then if you wanted to find the average value of j, of, you know, the age, what that would mean is that you're going to, you'd have to add every single age of everybody in the room. And since you have n of j people of age j, that's just n of j times j for that particular age or position or whatever you want to think about. And then you want to divide that by the total number of things that you counted, and that's just the average. And so if you look at that, that is actually just j times the probability of j. So then if you were to look at something like the average age squared or some sort of function of it, you would put in the age squared times the probability of finding the particular age without squaring the actual age itself inside of the probability, because that ends up meaning nothing if you do that. So generally speaking, the average value of any function of whatever it is that you're looking at will be that function times the probability of that particular value. So if we take this from the discrete case to the continuous case and let the difference between each value shrink to nothing, then you end up getting an integral, and you have the same arguments there. Yes, I think that would still be j. So with a wave function, if you were to try to find a particle between some positions a and b, the integral of the wave function squared will give you that probability. And again, we have the normalization constraint that if you look over everywhere that the particle could possibly be, it's going to have to be somewhere, so you're going to find it. So the expectation value of like a position, let's say, of a wave function would be the integral over all possible space times the value of the thing that you're looking for and the probability of finding it at that particular place. So then if we generalize that to any sort of observable that we can think of, you know, this is basically a function of x or something else if you'd like, then we just have to sandwich that operator in between the two wave functions. And the only real justification that I can come up with for that is that these wave functions are vectors, and this is a matrix. This is a column vector, and this is a row vector, so if you were to pull the operator out from here, then that would not make any mathematical sense anymore. I can't really come up with a physical interpretation of why it has to be in the middle. And then if you were to look at anything in 3 dimensions instead of a 1-dimensional space, you just need to integrate over all space instead of just the 1 dimension. And that's it.
Okay, let's thank the speaker. And there is a chance to ask questions. Questions 1. Question, please.
How do you get so good at explaining things, man? That was awesome.
I
really have
well, I've taken quantum mechanics 1 and 2, and I'm a math and physics major, so I've done functional analysis too, which explained all the things that made no sense to me at all when I took quantum, like why you can do the things that you do. So I have a little bit of experience with this stuff.
Well, that was my pseudo question.
More questions or more excited comments? So, what's the difference between statistical average and quantum mechanical expectation value? It is a provocative question.
The statistical average would be the average over one particular system, and the quantum mechanical expectation value is it would be that average value but taken across many different systems that are all identical.
Would you already decide and agree with me that it is opposite?
What then?
Would you agree that it is opposite? Statistical is over many systems and quantum mechanical is over one?
I guess when I took quantum mechanics, and the way that Griffiths explains it in his book, is that the expectation value should be interpreted as...
Then you should open discussion and start arguing. So there is a big counterintuitive component in quantum theory, and what London has presented is an attempt to bring quantum mechanics to our intuitive understanding about people in the room with different ages. But it is an attempt to speak about several systems, an ensemble, which is a statistical physics or mechanics. But quantum theory would work even for isolated systems. So in order to expand your explanation to truly counterintuitive quantum system, we should pick up a person who is in a superposition of like age being 23 and 24 years old. Maybe like, it's a very poor connection, but maybe a person at the midnight before the birthday, when he doesn't know or she doesn't know how old he or she is. So results of measurement can give both either this or this